these. Okay. Question 8. All right. So that one is, oh, that's the system of differential equations. Okay. So yeah, we can talk about it. So I think there was there's an example in the notes, if I'm incorrect. But all right. So we have number 8. We have x prime is equal to x plus 4y, and y prime is equal to 2x plus 3y. All right, so this is actually a taste of chapter 9 that he's introducing. And so what we actually want to do is we want to write this in vector notation. It's like the following, right? So essentially we have x prime, y prime is equal to 1, 4, 2, 3 times xy, right? And then, okay, so what is this? Well, you can think of this as the following. This is like some vector, right? This is like some vector v. This is some matrix A, and then, or this is like v prime, and then this is some other vector v. Okay, so this is like v prime is equal to av, and the way you can solve this system of equations, right? It's almost like if you had a system of equations, or if you had just a differential equation that was like y prime is equal to like some kx, or something like that, right? Y prime is equal to ky. It's very similar in that it looks like the same, except what we have now is that we have vectors instead of, we got vectors and matrices instead of, you know, a function and scalars. So the way to solve this is you actually want to find the matrix exponential of that matrix right there. So yeah, so you want to find either the AT to solve it. Actually, no, that's one way to do it. You actually don't have to. So what you want to do is step 1 is going to be the following. You want to find the eigenvalues and eigenvectors of this matrix here. So do any of you have this? Or is this... I mean, this shouldn't be too bad, right? So determinant of this, lambda squared, minus lambda, minus 3 lambda, plus 3, minus 8. So that's, or what is this? Lambda squared minus 4 lambda minus 5. Okay, and so this is lambda plus 1, lambda minus 5. And then, so lambda is equal to negative 1 and 5. Okay, and so now what you want to do is the following. So now you look at lambda is equal to negative 1. You get 2, 4, 2, 4. So what's an eigenvector for this? Not quite. So I have 2, 4, 2, 4. So you want to look at the rows, not the columns. Well, 1, 2 makes the second entry too large, right? So I think you're almost there, but it's negative 2, 1, right? Because you want to find. Oh, okay. Yeah. That's fine. Yeah. You said 1, 2. Yeah. So negative 2, 1. Okay, and then so that's an eigenvector, and then what else? Now you want the eigenvalue. Lambda equals 5. So 2, negative 2, 2, negative 2. Oh wait, hold on. This is negative 4, 4, 2, negative 2, and then this one is 1, 1. Yeah. So this is the eigenvector. Okay, so now you have your 2 eigenvectors and your 2 eigenvalues. So what the general solution to this system looks like is the following. The general solution to a system differential equation looks like y is equal to c1 e to the lambda 1t times the vector v1 plus c2 times e to the lambda 2t times this second eigenvector. Okay, yeah, so what you do, you just plug them in. So C1, lambda 1 is going to be our first eigenvalue. It doesn't matter what it is, so let's just say it's that guy. So this is going to be e to the negative t, and then you multiply it by the eigenvector associated with it, so that's negative 2, 1. And then you add it to C2 times e to the, okay, so now we need the second eigenvalue. Let's make that 5, so that's 5t. And then v2 is the second eigenvector, which is that, 1, 1. And so technically you're like done here. You can just leave it like this. But you can also write it as a vector as well. So we can do, so this is technically like a y vector. But if you write it as a vector, then you just combine the terms. So for example, this top term is going to be negative 2 times c1 e to the negative t plus c2 times e to the 5t. So c1 e to the negative t, or negative 2 times that, and then you add it to c2 e to the 5t. All right, and then you also have like a bottom term, which is going to be like that, and then it's going to be that. So that's just c1 e to the negative t plus c2 e to the 5t. And so either like this up here or this down here, it doesn't matter what form you leave it in, they're both considered like correct answers. Yeah, you don't have initial value conditions, right? Okay, yeah. So if you don't have initial value conditions, then you never have to solve for the unknowns. Yeah. So that's how you do that problem. So this is actually this is what you do in chapter 9. But we can do it now, because if you look at it, all you do is just find eigenvalues and eigenvectors. Okay, that's number 8. Any other questions? Let's see. So there are a few viewers on Twitch. I actually have the chat open, so if you want to type stuff in the chat, I'll read off of that as well. All right, I'll just leave this here. Whoa. Okay. Yeah. Right. Let's see. So yeah, okay. So in this case, and so we haven't introduced it yet, but there are eigenvectors, and then there are these things called generalized eigenvectors, and we have generalized eigenvectors if it's not diagonalizable. So if it just says eigenvector, I think you're okay with assuming that it is diagonalizable. Yeah, so yeah, you would just show it with the definition, AV equals lambda V, and then you have a to the 5th V. You know, you want to show that it's the same V. Which shouldn't be too hard to show. We can actually do this one real quick. So this is 1 H, right? Yeah, so you know V is an eigenvector of A. So this means that AV is equal to lambda V, right? And so how are we going to get a to the fifth, right? Because we want to show, right? We want to show that V is an eigenvector of a to the fifth. So then a to the fifth V is equal to some lambda, I don't know. Let's just call this lambda 0, and this is lambda 1 times V, right? Okay, and then, so we know this is true. This is what we know. So if we start off at AV is equal to lambda V, lambda not V, right? How do we get to a to the fifth V? No, so you don't. So this is what we want to show, right? We want to show that a to the fifth V is equal to some lambda 1 times the same V that we had before. Okay, so on this side we have AV, and we need to get to a to the fifth V. All right, so what's a good way of doing that? Well, one way you can do it is if we just keep on multiplying A on the left of this equation, right? So you get something like the following. So now you'll get like AAV is equal to A lambda not V, right? And then what is this? Well, now I get A squared V is equal to lambda naught times AV, right? And then what is AV? Well, AV is lambda naught V from here, right? So now this is equal to lambda naught V. So this is lambda naught squared V, right? So now you get A squared V is equal to lambda naught squared V, right? But we want to get to a to the fifth. All right, and so what we're going to do is then we are going to continue multiplying, right? A's over here, right? And essentially we need 3 of them because we need to get to a to the fifth, right? And if you do this, you should get that a to the fifth V is equal to lambda naught to the fifth times V, right? And then, so what does that mean? Well, lambda naught to the fifth, this is just a scalar, right? It's some scalar raised to the fifth, so we can just give it another name, and we'll call this lambda 1, right? And then this is the same V as before, we never changed it, so now we got a to the fifth V is equal to some lambda times V, right? And that V never changed. So, yeah, so this one should be true. Okay, so from Twitch chat, got question 7 and question 9. So let me pull those up. Okay, number 7. Okay. Okay, so number 7 is one of my favorite problems to do, or one of my favorite problems of this section. I think Nibby was the one that came up with these kinds of problems. Actually, no, Nibby taught for the professor that came up with this type of problem. But you have A is a matrix that's just all 2019. Right? Actually, let's see. Yeah. Okay, instead of writing 2019 over, I'll do it with different numbers, but the idea is going to be the exact same. So let's say these were all 3s. Right? So instead of having to write 2019 a bunch of times, just imagine everything is a 3. Okay, so the idea is going to be the same. The numbers are going to be work out a little differently at the end, but the main idea is similar. Okay, what's going to happen is we're going to use the fact, because you don't want to actually compute the eigenvalues, or computing the characteristic polynomial is too hard, right? because it's a 5 by 5 matrix and no one wants to take a determinant of a 5 by 5 with like lambdas and whatever. So what's going to happen is the following. Actually, hold on 1 second. Okay, never mind. We're probably fine. So what's going to happen then is we want to use the fact that the trace of A is equal to the sum of the lambdas, and we're going to use the fact that actually this one is the big one. I don't think we need the determinant one. So we're going to use the fact that the trace of A is equal to the sum of the eigenvalues. And this will help us find all the eigenvalues of this matrix. So the first thing is the following, right? We want to note that so how do we find eigenvectors in the first place? Okay, and the way we find eigenvectors in the first place is the following, right? Remember, we looked at the kernel of A minus lambda I, right, for some lambda, right? And remember, the dimension of the kernel had to be greater than 0. Right. If the dimension of the kernel wasn't greater than 0, what would happen? Well, if the dimension of the kernel was 0, then the only eigenvector for that lambda would be the 0 vector, right? And I said in recitation, at least, that you should never put the 0 vector as an eigenvector because it's not, the 0 vector is not an eigenvector. So, all right. Okay, so for some values of lambda, we're going to have a non-trivial kernel, right? And if we just look at the matrix presented to us right now up here, is there like an eigenvalue that you can just see, like that would give us a non-trivial kernel? Well, the idea then is this matrix itself, right, with all 3's in it, what's its rank? It's 1, right? And so the nullity is 4, right, by the rank nullity theorem. So what does that mean? What are we looking at in terms of A minus lambda I? What is our lambda here? Right, so here we have some nullity, right? The dimension of our kernel is already non-trivial, right? So this must correspond to the eigenspace of some eigenvalue, right? Because we said that as long as the dimension of kernel of A minus lambda I is greater than or equal to 0, then we can find eigenvectors, right? So in this case, the nullity is equal to 4, but remember, this is the nullity of the matrix A, right? So if I'm just looking at A, and I want A minus lambda I to be A, what is lambda? Lambda is 0, right? So note that since ker A is non-trivial, right? It's not just equal to the 0 vector. Lambda equals 0 is an eigenvalue. Because dimension of kernel of A, right? This is the same thing as saying the dimension of the kernel of A minus 0i. Right? So now here's your eigenvalue, right? This is lambda. And we said that this was equal to 4 from above, right? So, okay, so that means 0 is an eigenvalue, right? 0 is an eigenvalue, and what does the nullity tell me again? That tells me the geometric multiplicity, right? So I know that So for lambda equals 0, right, I know that the geometric multiplicity is 4. Okay. And now lambda equals 0 returns me just the same matrix, right, with all 3's everywhere. So I need to find how many vectors, how many eigenvectors, linearly independent eigenvectors do I need to find here for lambda equals 0? 4 of them, right? So, yeah. So dimension, right, of the kernel of a minus 0I is equal to 4, right? So now is equal to the span of 4 vectors, and so I need to find 4 vectors. Okay? And so what are the 4 vectors? They're going to, oh, that's 5. So they're going to be the following. It's going to be like 1, -1, 0, 0, 0, right? That's going to be an eigenvector, because remember, these are all 3's. And then another one's going to be like 1, 0, -1, 0, 0, right? And then you just keep moving that -1. So then 1, 0, 0, -1, 0, 1, 0, 0, 0, -1. Okay? So now here are 4 eigenvectors for lambda equals 0. Okay? And now, okay, so now we found 4 eigenvectors for lambda equals 0. Now we need to find the other lambda, right? Or is there another eigenvector? So first of all, right, why isn't the algebraic multiplicity of lambda equal to 5? Right? So why is algebraic multiplicity of lambda equals 0 not 5? Right? Because I think I said that, well, okay, so I said the following. I said that the geometric multiplicity was greater than or equal to the algebraic multiplicity, right? Or is less than or equal to the, wait, hold on. Yeah. So the geometric multiplicity is less than or equal to the algebraic multiplicity. All right. So I claim that lambda equals 0 has geometric multiplicity 4, right? But we don't know if this is equal to the algebraic multiplicity of lambda equals 0 because we never calculated the characteristic polynomial in the first place. Okay? So I have no idea how many roots of lambda equals 0 are inside of so I don't know how many times lambda equals 0 shows up as a root of my algebraic of my characteristic polynomial. Okay? So the idea is, all right, since geometric multiplicity is less than or equal to the algebraic multiplicity, in this case we know that lambda, in our case we have 0, we have lambda equals 0 has geometric multiplicity 4, so it's less than or equal to the algebraic multiplicity, so which can be 4 or 5. Right? So the algebraic multiplicity has to be 4 or it has to be 5, and it can't be any other number because this is a 5 by 5 matrix. So the algebraic multiplicity can't be greater than 5. So here are my two choices. I'm limited to the algebraic multiplicity of lambda equals 0 being 4 or 5. And why can't it be 5? Well, I said at the beginning that we want to use the fact that the trace of A is equal to the sum of the eigenvalues. Okay? So what would happen if the algebraic multiplicity of lambda equals 0 were 5? So I guess the other way to word it is, right, how many eigenvalues can we have in a 5 by 5 matrix? And the answer is 5 eigenvalues, right? Because I can have one for each like column or row, or that's the way you can think of it. So if lambda equals 0, right, if lambda equals 0 has algebraic multiplicity 5, right? What would that mean? Well, that means that every eigenvalue is 0, right? So then what would the sum of my eigenvalues be? 0, exactly. Then the sum of the lambdas is equal to 0, right? But what is the sum of the eigenvalues equal to? It's equal to the trace of my original matrix, right? But what is the trace of my original matrix? It's 15, exactly. Right? But we know that the sum of the eigenvalues must be the trace of the original matrix. All right? So this implies then that lambda equals 0 can't have algebraic multiplicity 5. All right? So therefore, lambda equals 0 must have algebraic multiplicity equal to 4. All right? Because it's 5 or 4, and if it's not 5, then it has to be 4. All right? And so since lambda equals 0 has algebraic multiplicity 4, this is equals, right? This is equals, right? So we get 4 is equal to 4. So we know that, okay, so for lambda equals 0, our geometric multiplicity and the algebraic multiplicity are equal to each other. So that's good, because that means it should be diagonal. Oh, well, it hasn't failed the diagonalizable condition. Okay? So now we need to find the other eigenvalue, right? And we kind of have it already, right? Because if lambda equals 0 has algebraic multiplicity 4, then I add 0 4 times, and I still get 0, right? But the sum of my eigenvalues has to end up equaling the trace of my original matrix, which was 15. So what does the last eigenvalue have to be? Yeah, the last eigenvalue has to be 15, right? So the last eigenvalue is lambda equals 15. And then so what you'll get is you'll get like negative 12, 3, 3, 3, 3, 0, 3, negative 12, 3, 3, 3, right? Etc. And then you get negative 12 here. And what's the eigenvector for here? Well, the eigenvector is just 1, 1, 1, 1, 1. Right? If you look at it, negative 12, and they got 4 3s, well, if you just add them all up, you'll get 0, right, for every single row. And so now we have an eigenvector, right, for each unique eigenvalue of lambda. You have, for each unique eigenvalue, you have the algebraic multiplicity equal the geometric multiplicity. All right, so it's diagonalizable. And then here we even found all the eigenvectors, right? So then you can create your S matrix, and then your D matrix is going to be like 15, 0, 0, 0, 0 on the diagonal, right? And so, yeah, so this one is diagonalizable, and the one with the 2019, it's like the same thing. It's just the number's 2019, so the trace is going to be a lot larger, but the idea is like the exact same. So the tricky part, I would say, is this part right here with the with dealing with the lambda equals 0 case. So you really need to know why the geometric multiplicity is equal to the algebraic multiplicity, and how to rule out like any other cases. And you use it using the fact that the trace has to be equal to the sum of the eigenvalues. Okay, so that's 7. Okay, let me make sure chat hasn't said anything else. All right, so number 9. I'll do. Let's see, number 9. Okay, let me do A. Okay, so number 9. A. So you want to find e to the AT. And I think I got to this on Friday, but not on Wednesday. What it is, it's the following. So if you can diagonalize a matrix, it's really S e to the dt S inverse. All right, if A is diagonalizable. So okay, so A is equal to, in our case, 1, 3, 3, 1. So if we diagonalize it, what do we get? Okay, I think the eigenvalues are going to be negative 2 and 4, so that should be fine. All right, so lambda equals -2. Okay, so now I get negative. Okay, so -2, you get 3, 3, 3, 3. So this is a plus 2i. And then so the eigenvector is going to be -1 and 1. And then lambda equals 4, you get a minus 4i. So now your eigenvector is going to be, you get -3, 3, -3, 3, 3, -3. And so your eigenvector is going to be 1, 1. Okay, and then now, so first of all, just write out the diagonalization, SDS inverse. You'll get something like, right, -1, 1, 1, 1, -2, 4, and then -1, 1, 1, 1 inverse. Okay, so now to find e to the AT, right, is S e to the DT S inverse. And what D is, you just literally take your diagonal values and you just throw them inside an exponent times t. So you get, so the S matrix stays the same, right? The S matrix, oops, this is an SDS inverse. So the S matrix stays the same. And then now this middle matrix, this becomes e to the -2t, e to the 4t, right? So it was just the eigenvalues here. They just go inside your exponent. Multiplied by some t, and then S inverse. Okay, and I'm not going to multiply this out, but you should multiply it out. So if you multiply this out, you'll get the answer for e to the AT. All right, so e to the AT is equal to whatever the heck this is, and you're just going to have to leave like the e to the -2t's and the e to the 4t's, they're just going to have to like be in the final answer. So you're going to get like some constant times e to the -2t plus some constant times e to the times e to the 4t on top, and the same thing on the bottom as well. All right, so you have to find this inverse matrix, and then you have to multiply it all out. And so you do the exact same thing with B. And there he gives you the characteristic polynomial. I kind of just eyeballed the eigenvalues here because I knew I could use the trace trick, and this worked out well. But you should probably find the characteristic polynomial as well for part A. But yeah, so this is how you find the matrix exponential. If you want to see like me actually multiply it out, I do have YouTube videos on the matrix exponential. Okay, let me see. All right, 2 and 8C in the recitation homework. Okay. So number 2 on the recitation homework. Is the following. Okay. Number 2. The recitation homework. Okay, so yeah, so you have the map, right? That's the reflection across the plane. So R3 to R3 reflects across x plus y plus z is equal to 0. So on recitation homework 6, let's see, what did we ask you for on recitation homework 6? Let me pull that one up. Okay. So recitation homework 6, we asked you to find. Oh yeah, so we asked you to find a basis for R3 consisting of the vectors V and R3. So let me just show this. So this is what we found for recitation homework 6, right? So we literally told you to find a basis of eigenvectors in recitation homework 6. And what you should have realized was that they were 2 vectors in the plane, and then two vectors in the plane, and then the normal vector, I think, was the basis. All right. So for part A, So for part A, you have your eigenvectors already, which are two vectors in the plane. And the normal vector, right? And these two vectors in the plane, they have to be linearly independent, of course. So, all right, so those are the three eigenvectors. And then for the two vectors in the plane, right, I think I mentioned this briefly, or I mentioned this in recitation, but if you're reflecting two vectors in the plane, the vectors are just going to be reflected to themselves, right? So the eigenvalues associated with the two vectors in the plane are going to be lambda equals 1. Okay? And then the normal vector, right? So if you have a plane, you have a normal vector and it gets reflected to the opposite of itself, right? So this has an eigenvalue of -1. Okay? So if you want to find the map with respect to an eigenvectors, right? Then remember, when you diagonalize a matrix, A is equal to S D S inverse. A would be like A is like the map within the standard basis, and then S is like a change of basis matrix, right, from E to the eigenbasis that you have. And then D, remember, is the map inside of the eigenbasis, and then the S takes you back to standard bases, right? So I think I did these with a little different, like the names are a little different, but this is the general idea. So part A asks you to find the matrix of transformation relative to the eigenbasis, which is literally just the diagonal matrix. So so in this case, you can just say D, right? And so the diagonal matrix is just whatever your eigenvalues are. And since you have two vectors in the plane, one appears twice, and then -1 is the other eigenvalue. Okay? So D is, in this case, TBB with respect to TBB, where B is a basis of eigenvectors. Right? So that's fine. So that's part A. This is part A. Right? And remember, if you don't understand this part right here, remember this is covered in recitation 7. It's near the end, right? Okay, so that's part A. Part B is to find the matrix relative to the standard basis. All right, so essentially what you want to do is you want to find the matrix A. And so what you have to do now is you actually have to find some eigenvectors, and then you have to like multiply it out. So you have A, right, is equal to S D S inverse, and A is really, right, TEE with respect to the standard basis. So now what you have to do is you actually have to find a basis of eigenvectors times this D matrix, and then find the inverse of that. So again, so two eigenvectors in the plane and one normal vector. And since lambda equals 1 are in my first two columns, so this is going to be S, right? This is D, and then this is S inverse. So these two columns are going to be in the plane, and then so these first two columns are in the plane, and then this last column is going to be the normal vector, right? And so the normal is pretty easy. That's just 1, 1, 1. And then now we need to find two vectors in the plane. So essentially all you have to do is just find two things that satisfy the plane equation. Right? Or, yeah, so since 0, 0, 0 is a point in the plane, you can just have all your vectors starting at the origin and then going out to somewhere else, right? So all you have to do is find points that satisfy the plane equation. And so you can do something like 1, 0, -1, and then 1, -1, 0. Right? And so now you have SDS inverse, and what you want to do is you just have to multiply this out. And you'll get, it's not a great answer. There's like, it's going to be some, everything's going to be over 3. So it's going to be some fraction. There's going to be like a lot of fractions over 3, and that's going to be the answer to part B then. So this is part B. Okay. Let's see. 8C of the recitation homework. Oh god, this is the Fibonacci question, isn't it? Okay, one sec. So I want to find so 8C asks you to find a formula for m to the n and use this in part B. Okay. So you have m to the n. Right, so you want to diagonalize m, right? Because we tell you m is the following. So this is recitation homework 8C. So m is this matrix that we give to you, and so we want you to find m to the n. The annoying thing is that I believe the eigenvalues are like the golden ratio. It's like 1 plus or minus root 5 over 2. So what you'll get then is, so now you have like 1, so you have s, right, m to the n is equal to, okay, so step 1 is to diagonalize m. And then, so lambda is equal to 1 plus or minus root 5 over 2. And then, so you need to find S ds inverse. Okay, so let's see what this is. Let's try to find some eigenvectors. So this is negative 1 minus root 5 over 2, 1, 0, and then 1 minus 1 plus root 5 over 2. Okay, so this is a minus this guy times I. So what are the eigenvectors? Let's see. Oh wait, that's not a 0. Sorry, this is not a 0. This is a 1. Okay, so I think one of the eigenvectors you can do. So v1 here, the eigenvector, you can have 1, and you can just have the positive version of this guy as the second entry. So the 1 plus root 5 over 2. Okay, and then I think that should work. Yeah, pretty sure, because that kills off the first. That kills off the first row at least. So it theoretically that should kill off the second row as well. And then I just haven't worked it out, I guess, explicitly. And then the second eigenvalue, right, is 1 minus root 5 over 2. And so now you get a minus 1 minus root 5 over 2, I. And so now this is negative 1 plus root 5 over 2. And then this is 1, 1, and then you get 1 minus, in parentheses, 1 minus root 5 over 2. Right, and then the same idea holds. V2 should then be 1, and then the negative version of this guy. So that would be 1 minus root 5 over 2. Okay, so now I have two eigenvectors. We diagonalize m, right? So m is equal to S ds inverse. You can feel free to use like Mathematica or something to compute this, to compute S inverse. I think it's actually a pain in the, it might be a massive pain in the neck actually. So this is, I guess, 1 plus root 5 over 2, 1 1 minus root 5 over 2. And then D is 1 plus root 5 over 2, 1 minus root 5 over 2, and then S inverse, 1 plus root 5 over 2, 1 minus root 5 over 2. Right, so you got to take the inverse of S inverse at the end there, and just to make sure I have the right eigenvalues and eigenvectors. I think that's right. See if anyone is objecting on Twitch. Okay, doesn't seem like it. Okay, and then what now? So okay, so that's m, right? And then so for m to the n, that's equal to s d to the n s inverse, right? So you just have to take this middle matrix right here, and you just got to raise it to the nth power to get mn. So that's the first part of part C. And then to find the nth Fibonacci number, what you want to do is, okay, so the nth Fibonacci number right. Let's see. Let me see how we do this. I guess, which one do we consider? Okay, f0 is equal to 1. Okay, so to find the nth Fibonacci number, you want to find fn, right? And so there are two ways to do this. You know that xn is equal to fn and fn plus 1, right? So, and then from the previous, from part B, that's illegible. From part B, you know that xn is equal to m to the n times x naught, and I think we give you what x naught is. Or, well, x naught is 1, 1, right? Where x naught is equal to 1, 1, since this is the 0th Fibonacci number and the first Fibonacci number. Okay? And then, so now to find the nth Fibonacci number, it's just the first. So the nth Fibonacci number is the first row of xn, which is equal to m to the n times x naught. Okay, and then if you multiply this out, right? If you multiply m to the n with 1, 1, you'll get some equation, right? If you multiply m to the n and x naught, you'll get a vector, and then you'll take the equation in that first entry of that vector to find the Fibonacci number, the nth Fibonacci number. Okay. Okay, 10B and C. So I'm guessing this is then the regular homework. Okay, yeah, so the idea is going to be very similar, right, to what we just did in 10B and 10C. Actually, it's the exact same thing. So in part A, after you diagonalize M, right, 10B, this is regular homework. Right, so first of all, in 10A, just a quick hint, you actually did this already on your homework. The matrix, you actually diagonalize this matrix on your homework. It's somewhere there. You can just go look for it. And then, so you'll find, so in 10A, you get, right, SDS inverse. You get M is equal to SDS inverse. And so in part B, you want to find MN, right? But that's just S d to the n S inverse. Okay, so just take that middle matrix, the middle diagonal matrix, and just raise it to the nth power. And then multiply them all out. Okay, so the idea then is, for part B, you actually just have to, you have to multiply everything out, which, since it's an applied problem, You can use like Wolfram, you can use matrixcalc.org, you can use Mathematica, whatever you want. You don't actually have to like calculate this, right? And then the last part then is for part C. Now, since you know what this is, right? For part C, you still want Mn is equal to S d the n S inverse, but now you let n go to infinity. So the way you should do this as an applied problem is you should probably just like in whatever calculator you have, just like let n be a really large number. And then like just keep on trying to make it larger and larger in your calculator or in your like online or in your computer program and see what happens to Mn. It should like stabilize and end up running into like it should stabilize. I think that's what I'm trying to say. And the limiting distribution of n to infinity xn. So xn is the following. So then so xn, right, is the fraction, right? This is an, bn, cn in the nth generation. And you know from the previous homework that xn is equal to m to the n times x naught. Right? And then in part B of the previous homework, you actually computed this already, I guess. So I guess 10C is like the same thing as 14B from the previous homework. Actually, it's like the exact same thing. It's the exact same problem. Let me just make sure though. Yeah. So mn is equal to m. So yeah, so xn is equal to m to the n times x naught. So you find what m to the n is as n goes to infinity, of course, and see if you can find. So if you just let x naught be like a naught, b naught, c naught, I guess what you really care about is you really care about what mn is equal to when this gets really large. Okay, this problem shouldn't be too much work, especially since like you do part A already in the homework, and then everything else is just you plug it into some calculator and you make n really big after you diagonalize it. Okay. Number 6 on the recitation homework. Number 6, which is that one? Okay. Wait, does this one still have does it still say in part B that the eigenvalues may not be explicitly determined? Okay, that's a typo. That shouldn't be there. You can actually find all the eigenvalues. So we changed the problem up slightly for number 6. Okay, so recitation homework number 6. Oh, it's not the color I want. Okay, recitation homework number 6. Okay, so part A is what is the size of A? Well, so there's a few ways. So what you want to do is you want to do something like A x is equal to B, right? And then you can like try to figure out the dimensions this way. Okay, so you know that the system, right, AX equals 3, 3, 3. So this is a 3 by 1. Okay? And then that means x, then this has to be 1 as well, right? Because this is m by n, this is n by p, then this is m by p, and you know here this is 3 by 1. So, well, m then has to be 3, and p has to be 1, right? So we know that much so far. So now we need to figure out what n is. And n is the number of columns, right? So n is the number of columns. And the way we can figure that one out then is by the rank nullity theorem, right? So rank nullity theorem says that rank plus nullity is equal to the number of columns, right? And then the rank is 1. That's given to you in the problem, right? And what's the nullity? Well, I give you 2 vectors in the kernel, right? So the nullity has to be 2, since I tell you what the kernel of A is. All right, and so it looks like the number of columns is 3. So then it looks like n is equal to 3. All right, so now A is going to be 3 by 3. Okay, so that's part A. So yeah. Yep. Yeah, no, yeah, you could have done that as well. Yeah, that was fine. Yeah, because if it's a solution to the system, then it has to, the dimensions have to work out. Yeah, so you could have done that too. All right, so that's part A. A is 3 by 3. Part B is the following. Part B. Okay, find the eigenvalues and eigenvectors of A. So this is really similar to that matrix of all threes problem that we did. Remember, so the kernel of A is equal to the kernel of A minus 0i, right? This is really important. Because, remember, because 0i is just the 0 matrix. So essentially what we have here is that we have lambda is equal to 0. Right? And since I tell you that the kernel of A is equal to the span of 2 vectors, right? What are these vectors here? They are eigenvectors for lambda equals 0. Okay? So these are eigenvectors for lambda equals 0. They also happen to be eigenvectors in the kernel of A that span the kernel of A. But the kernel of A is the kernel of A minus 0i, right? Which is what we have written here. So they're the same thing, all right? Okay, so those are 2 eigenvectors right there. We have 2 eigenvalues, lambda equals 0 with multiplicity 2, or geometric multiplicity 2. And so we just have to make sure that the algebraic multiplicity isn't 3, right? So A is 3 by 3. And so we want to make sure that algebraic multiplicity isn't 3. Okay, the way we do this then, well, now we can use the fact that the solution of the system is 1, 1, 1, right? So what we have now is then now we have A times 1, 1, 1 is equal to 3, 3, 3, right? But what is that? Well, this looks suspiciously like the definition of eigenvalue and eigenvector, right? Where if we pull out a 3 from the right-hand side, right, it's A111 is equal to 3111. Well, that's just quite literally AV is equal to lambda V, right? So now from this, we find that, okay, lambda here is 3, right? Because AV is lambda V, and then V is equal to 111. Okay, so now we found 3 eigenvalues. One's repeated twice, and then we have 3 linearly independent eigenvectors. Okay, and now part C, find the matrix A. Well, since the geometric multiplicity is equal to the algebraic multiplicity for each eigenvalue, and the geometric multiplicity is equal to the algebraic multiplicity for each eigenvalue. That's quite a mouthful. now we want to find A, and how we can do that? Well, we can diagonalize our matrix, right? So A is equal to SDS inverse. You have your eigenvalues here, right? This is 0 multiplicity 2. Well, this was geometric multiplicity 2, but algebraic multiplicity is also 2 because we have a different eigenvalue here. And then you can diagonalize your matrix, and then you can just say, okay, A is equal to SDS inverse. Multiply that out, and you'll get A. So that's part C. Okay. All right, number 3 on the recitation homework. Okay, recitation homework number 3. A squared is equal to negative A. Find all possible eigenvalues of A. Okay. So with this one, what we wanted to do is to make you use the definition of eigenvalue eigenvector. And let me hold on one second. Okay. So what you want to start off with is the following. So AV is equal to lambda V is the definition of eigenvalue eigenvector. And if you know that A squared is equal to A, all right, what can we do? Well, you just want to play around with this definition a little bit. So this is the definition. And so if we multiply both sides by A, right, AAV is equal to A lambda V. And now you get A squared V is equal to lambda AV. Okay, but what is lambda V? What is A times V here? This is just lambda V, right? Because of that definition. So now you get A squared V is equal to lambda times lambda V, right? So A squared V is equal to lambda squared V. All right, but here's the thing. We also know that A squared is equal to negative A, right? So then this is also equal to negative AV. Right, since A squared is equal to negative A. Okay, so what does that mean? Well, what is, if we just look from this side, what is negative AV? This is, well, negative AV is negative lambda V. Right, because it's, you can just look at AV, that's lambda V, and then you put the negative sign out in front. So now you have A squared V is equal to lambda squared V, which is also equal to negative lambda V. So what we essentially have is we have the following relationship. Lambda squared V is equal to negative lambda V. Okay? And so what is that? Well, then you know that lambda squared is equal to negative lambda. So what are the possible eigenvalues for this? I think you can have, so you just need to have something that satisfies this condition, right? If you do factor it over, lambda squared plus lambda is equal to 0. And so now the only eigenvalues that satisfy this, you can have lambda equals 0. Or you can have lambda equal to, looks like negative 1. Okay, and so these are the only possible eigenvalues that satisfy. So if you have a matrix that satisfies this condition, with AV is or A squared is equal to negative A, then the only eigenvalues of that matrix have to be 0 and negative 1. Okay, and this is actually, we could actually like make you create a matrix that has this property. I think any. Actually, no. Actually, that's. I'm lying. I think. I have to think about how that works, but we can theoretically ask you to like recreate this backwards on an exam, right? Just be like create a matrix that has A squared is equal to negative A, and you can start with the eigenvalues, eigenvectors, and make it that way. But I have to think if that actually like makes sense, doing it that way. Okay, so that's question 3. Any other questions? Actually, that's the entire list on Twitch. Yeah. Oh, okay. Someone just asked that too, so perfect. Number 4. Oh, that's homework 8. Okay. So I guess it's the same thing as the plane, right? It's very similar to the plane problem, except now instead of in 3 dimensions, we're in 2 dimensions. So number 4 on the regular homework. So you know A is equal to 0, 1, 1, 0, and so he says that this reflects each vector across the line y is equal to x. So here is your xy, and here is the line y is equal to x. Okay, so we want to reflect stuff across this line. So it's the exact same thing as the plane question, right? What we need to find the vectors that when we reflect it across this line, they just become stretched versions of themselves, right? So the idea is similar, right? Remember how we found the ones on the plane? We found 2 vectors in the plane, and then we found the normal vector to the plane. So why did we find 2 linearly independent vectors in the plane? Well, that's because the plane is 2-dimensional, right? In this case, since the line is 1-dimensional, we only need to find 1 vector on the line, which is very easy to do. And then the other thing we need to find is the normal to the line, which also shouldn't be too hard, right? Because it's just a perpendicular vector to the line. So yeah, so right, my eigenvectors are going to be 1, a vector on the line, right, and 2, the normal to the line. Okay, so, well, what is a vector on the line? The line is y is equal to x, so a vector is just going to be 1, 1, right? Okay, and then what is the eigenvalue associated with this vector? Well, it's on the line, it gets reflected, and it's still on the line, right? So in that case, it stays itself, so lambda is equal to 1. And then you want to find the normal to the line, so that's going to be, right, so if you have this vector right here, right, that's perpendicular, and then you reflect it over the line, right, that just becomes a stretched version of itself, but in the opposite direction. And so what is that? Well, just find the perpendicular vector to 1, 1, And so in this case, I think it's negative 1, 1, right? Or 1, negative 1, they both work. And then what's the eigenvalue? Well, it gets flipped over the line, so the eigenvalue is negative 1. So it's just a two-dimensional version of the plane problem. Yeah. Okay. Any other questions? Yeah, I think so for the whole thing with like the nullity, like the kernel of a minus 0I, like where is it? It's not loading. Yeah, so all the stuff that we did with like the kernel of a minus 0I, whatever, if you go to a prep, so I wanted to get to this, but I didn't get to it. I might cover this over the weekend or when we get back from break. But yeah, so here's like written out notes that I wanted to talk about in recitation last week, but I didn't get to. So at the end of my recitation 6 prep, there's stuff about lambda equals 0 that I talk about. And so this is the stuff where you realize that, hey, look, the kernel of A is the same thing as the kernel of a minus 0I. And so you can talk about, right, nullity of A is the geometric multiplicity of lambda equals 0, which is less than or equal to the algebraic multiplicity of lambda equals 0. Again, I might talk about this when we get back from break. I think it's a worthwhile thing to do. Okay. Question 7. Confused about how you wrote the span of the kernel. Wouldn't the negative ones be the first term in each element of the span? So was that was the big matrix, right, with the 5s? It doesn't matter as long as, so I was just eyeballing vectors in the kernel. So let me pull that up. Okay, sorry, 1 second. My app's being slow. I'm going to reload it real quick. Okay. There we go. Oh no. Oh no. Alright, we killed all of them. If you go to, okay, officers. So question 7, you're asking why aren't the, yeah, so you're asking why are these not negative ones? It doesn't matter. Because, so why would the negative ones be the first term? Yeah, so if you do the dot, if you multiply the 3's out with these vectors, you're going to get 0 regardless, right? It doesn't matter that these terms aren't negative 1. As long as one term in the vector is negative 1 and the other term is not negative 1, they're going to cancel out. Because if we do the dot product, right, 3, 3, 3, 3 times this, you get 3 minus 3, and then everything else is 0, right? So in that case, then you get 0, right, which is what an eigenvector needs to satisfy. And then the same thing holds for every other vector that I wrote in the span. Okay, so it doesn't, so if I did write these as negative 1 up here, then all these would have to be positive. They're the same vectors, they're just multiplied by negative 1. Okay, so yeah, so that this kernel that I have in red also works. But I'm going to remove that. Okay. Any other questions? Yeah, so hopefully it's like manageable. The recitation homework, it was a bit long, but I guess at least the true false part you don't have to justify. And then yeah, but a lot of this is just the same repetitive stuff with like diagonalizing the matrix and like realizing what you need to do with the diagonal matrix. So yeah, it's just really hammering in the fact that you need a lot of theory stuff, I guess. But it should be enlightening, some of these things. Like, for example, number 5, he actually proved for diagonal matrices that the sum of the trace is the sum of the eigenvalues, and then the determinant is the product of the eigenvalues. Okay, can you do 6? I'm guessing that's the regular homework. Regular homework 6. Okay. So you just want to determine if it's diagonalizable or not. This one should be pretty straightforward. Unless you mean recitation homework 6, which I already did that one, right? Yeah. Okay. So number 6 on the regular homework. Oh God, this is really slow. Okay. All right, so A, 1, negative 2, negative 2, 2. So find the determinant of A minus lambda I. 1 minus lambda, negative 2, 2, 2 minus lambda. And then this is lambda squared minus lambda minus 2 lambda minus 4. Okay, and then this is lambda squared minus 3 lambda minus 4. Okay. I remember this one, I think. Wait, hold on. I'm missing a plus 2. Okay, so this is minus 2. Okay, I think this one is the one that doesn't factor nicely. So I don't think this factors right here. This characteristic polynomial. So yeah, so you gotta go to 3 plus or minus square root of 9 minus 8. Hold on. Plus 8 all over 2. Right, so that's your quadratic formula. So these are your roots. You have 2 of them. All right, so that's 3 plus or minus root 17 over 2. All right, so those are your roots of your polynomial. Let me just make sure that's right. So the determinant is 7, yes? No, it's 6. So you get 2 plus, no, determinant is negative 2. I'm talking about. Okay. I think that's right. Negative b plus or minus square root b squared minus 4ac. Okay, yeah, that's right. And then, so these are your eigenvalues. So now you just gotta do them one at a time. And then, so what do you get on this first one? You let lambda equals 3 plus root 17 over 2. So then this is a minus 3 plus root 17 over 2I. And so this is, oh god, this is negative 2 minus root 17 over 2. And then this is negative 2, negative 2, and then this is negative 1 minus root 17 over 2. Okay. Let's see. Okay, so what are the eigenvectors? Well, can't really eyeball this one. So what you want to play around with is you want to play around with the conjugates of the square root 17s. So if you let v1, I'm just going to let this first term be 2 plus negative 2 plus root 17 over 2 and see where that gets me. All right, so if I take this first row and I multiply it with this eigenvector, I'll get negative 2 minus root 17 over 2 times 2 plus root 17 over 2 minus or plus a negative 2 times some number. Let's give this something. Let's call this like q, right? And that's equal to 0. Okay, so we really need to just solve for q here. And what do I get? Well, okay, so this becomes negative 4. The reason why, oh, that's a negative 2. So this is a positive 4. The reason why you want the complex conjugate is because they cancel each other out. Or at least like those square root 17 terms cancel each other out, and then you're left with minus a root 17 times a positive root 17. And then if you multiply them together, you get minus 17. So you get 4 minus 17, and then, okay, so you get that, and then divided by 2. All right. So this is negative 13 halves minus 2q is equal to 0. And then, so 2q is equal to negative 13 halves, and q is equal to negative 13 over 4. So it looks like q is negative 13 over 4. Okay. This doesn't seem very promising. And then we'll just check to make sure that's right. So then now you get negative 2, right? So now you want to check with the dot product with the second row with this guy. So you get negative 2 times negative 2 plus root 17 over 2. And then you add that to negative 1 minus root 17 over 2 times negative 13 over 4. Yeah, this isn't... 4 plus 4 minus 2 root 17 over 2. So I guess they cancel. This is just 4 minus root 17. And then, yeah, okay. That's not going to cancel. So let's see what they do wrong. Is this root right? All right, I'm going to let Wolfram Alpha calculate these eigenvalues for me. Just to check. It should be right. I don't think I did anything wrong. Lambda squared minus lambda minus 2 lambda plus 2 minus 4. So that's that. Negative b plus or minus square root of b squared plus minus 4ac, but there's a minus sign, over 2, so that's root 17. 3 minus root 17 over 2. Oh, I know what I did wrong. Okay. No, never mind. I know what I did wrong. Okay. Be careful when you're subtracting these guys, because this is like 3 plus root 17 over 2. So everything's over 2. not just the root 17 over 2 term. So this is really, when I do 1 minus this, it's really 2 over 2 minus that. So this should be a negative 1. And then when I do the term on the bottom, it should be 4 over 2 minus that. So this should be a positive 1. Okay. All right, so it's just addition error. It's fine. So the same idea holds. You want to work around it with the conjugate. Okay, so yeah, so for this first term, you still just make it the conjugate of that nasty root term. Okay, and then, so now you get negative 1 minus root 17 over 2, and then multiplied by negative 1 plus root 17 over 2, and then you added that to negative 2 times some q is equal to 0. Okay, what's this first term? Get 1 squared. Right, you get 1, negative 1 squared is 1, minus 17 over 2, plus negative 2q, or minus 2q, is equal to 0. Okay, this term is negative 8, so negative 8 is equal to 2q, q is equal to negative 4. Alrighty, and so now we use the second term to check. So now you could do negative 2 times the first value, which is 1 plus root 17 over 2, negative 1 plus root 17 over 2. And then the second term is negative 4. Okay. And then that, okay. Anyways, negative 4 plus negative 4 times or 1 plus 1 minus root 17 over 2 times 4, negative 4. Okay, that doesn't work either. What am I doing wrong? Doing something wrong here. Q half. It should be a negative 2, because if this were negative 2, one, 2, 1 minus 3. Right. So it's negative 1 over minus root 17. That's fine. And then 2 is 4, so you get 1 minus root 17 over 2. That's fine. That's fine. Negative 1 minus root 17, negative 1 plus root 17. It's negative 17. That's positive 1. Oh, this is over 4. Oh my god. Okay, yes, the denominator should be over 4, right? So, just some silly. Okay, well, denominator's over 4. Because both these terms are over 2. I like added them, right? You're supposed to multiply them. So, yeah. Okay, so now you get negative 4 is equal to negative 2q. Q is equal to negative 2. Okay. All right, I am certain this is right. So that's going to be your first eigenvector. And then, because if you make this a negative 2, it works out fine. So that's equal to 0. That's good. And then the other eigenvalue vector is the same thing. Lambda is equal to 3 minus root 17 over 2. So now a minus 3 root 17 over 2i is the following. So this was a 1 minus, so the negative 2 plus root 17, or negative 1 plus root 17 over 2, and then negative 2, and then this is 2 minus that, so this is 1 plus root 17 over 2. And same idea, so let v2, 1 minus root 17 over 2 on top. Okay, and then we'll let this be something on the bottom. Again, let it be q for now. So negative 1 plus root 17 over 2 times negative 1 minus root 17 over 2. Okay, and then you got that. Minus 2q is equal to 0. All right, this is 1 minus root 17 over 2 again. Okay, so this is 1 minus 17 over 4 is equal to negative 2. Q is equal to 2q. So you get q is equal to 2, or q is equal to negative 2 again. And that does sound about correct. So this should be your other eigenvector. As you'll notice, it's just the conjugate. The first term, there's a conjugate. It's the conjugate of the first term, right? So that minus sign, that plus sign just become a minus sign, and then everything else stay the same. That is consistent with what you would expect. So those are two eigenvectors, and then diagonalizing it from there. Pretty simple, but I guess it's just the eigenvectors that are a big pain to find, as we can tell. And then okay, the other one. Okay, B. What is B? B 1 0 0 0 1, I think, and then three 7 1 negative 3. Okay, what you want to do here is the following, right? Det a minus lambda I, 1 minus lambda, 0, 0, 0, 3 minus lambda, 7, 1, 1, negative 3 minus lambda. Cofactor expand along the first row makes it easy-ish. Okay, and then you get 1 minus lambda times the determinant 3 minus lambda, 7, 1, negative 3 minus lambda. Okay, 1 minus lambda, and then this is lambda squared minus 3 lambda plus 3 lambda minus 9, and then this is minus 7. Okay, so this is pretty good. So 1 minus lambda, lambda squared minus 16, so lambda then is equal to plus or minus 4, and then 1. And then eigenvector should be pretty easy from here. So lambda equals 1, 0, 0, 0, 0, 2, 7, 1, 1, negative 4. Okay, let's see. What's the nullity here? You could do... Okay, so from this row, you can tell immediately what the second and third entries are going to have to be. So if we make this one like so this entry has to be 7, and this one has to be 2, and then one of these has to be negative, and you can choose. Let's make this one negative. Okay, and then so that makes that row 0, right? Because it doesn't matter what this entry is. And then now we have to look at the last row, right? And so now we got, like, if that's q, we get q plus 7 plus 8 is equal to 0. So it looks like q is equal to negative 15. All right, so that's one of the eigenvectors. This is actually a matrix that was on last year's exam for my section. I recognize this eigenvector. All right, and then plus or minus 4. So lambda equal to 4, negative 3, 0, 0, 0, negative 2, 7, 0, 0, negative 7. Wait, hold on. Hold on. That's not right. So this is 1, 1, negative 7. This is a negative 1. Okay. So same idea. I think this one, though, is a little easier to find because this first row tells you immediately that this first entry has to be 0 because there's nothing to kill off the 3 otherwise. And then 7, 1 finishes that one off. And now lambda is equal to negative 4, 5, 0, 0, 0, 7, 7, 7, 1, 1, 1. Right, and it's the same idea. This first entry has to be 0 because there's nothing to kill the 5 otherwise. And then 1, negative 1 does the job there. Okay. And yeah, so that should be diagonalizing. You should be able to find those diagonal matrices then. Well, that was a lot more computation than I was expecting. Okay. Any other questions? Nothing new in chat. Right. Yeah. So I think a lot of it just comes down to just doing it a lot. But what you want to do essentially is you want to zero out rows. So I guess we can just look at this right here. So like the kernel for this matrix right here, right? What I want to do is be able to zero out every single possible row. Okay, so essentially what I'm doing is I'm taking a dot product of the row and the column vector, right? Since I'm multiplying them. So whenever you just have like a single value, right, in the row, there's going to be nothing else that can essentially cancel this guy out, right? So that means the entry associated with wherever that value is located has to be 0. So since this first value is -3, then this first value in my column vector has to be 0, right? Because otherwise I won't be able to kill it, right? So that's fine. but that doesn't tell me information about the other two entries, right? So to find information about the other two entries, I have to look at the other rows of the matrices. And so now we turn to, let's say row 2 or row 3, doesn't matter. But what I want to do now is I want to find something that can kill off, right, such that the dot product is equal to 0. So if I see a negative 1 and 7, then I know that if I multiply this guy by 7 and this guy by 1, all of a sudden I got minus 7 plus 7, and that's going to get me 0. Okay? So I put 7 and 1 in there, and then now I just pray that it worked down here. All right? And it does. So we know that's good. Okay? A more difficult one would be like the first one up here. I guess this is more difficult, but essentially the first row tells you absolutely no information, right? It's all zeros. So we can't use it. We can't use the first row to do anything since it's all 0. So we have to turn to row 2. And so now in row 2, right, I got a 2 and a 7. And so, well, if I multiply this by negative 7 and this by positive 2, right, then I'll be able to get negative 14 and positive 14, right? And so here I did it the other way around, but the idea still holds, right? I made the 2 a negative rather than the 7 a negative, but you had to make one of them negative. Okay, and then so once I have that, well, this still doesn't tell me anything about the first entry because there was a 0 there, right? So now, since I have a 7 and a negative 2, now I take those numbers and I go down here and I do the same thing. So now if I multiply this guy by 7 and this guy by negative 2, so let's just stay consistent. This will be 7 and this will be negative 2. So now here I get 7, here I get negative 8, but this is a negative 4 times negative 2. This is a positive 8, right? So now this is 15, and now I need something that for 1 times something to get me negative 15, right? Since I need to cancel out a positive 15. And so I choose negative 15 for my kernel up there. So that's how you do those. The other ones that are important to do would be the ones we did way earlier. Like these guys with the square roots and stuff. Remember how I did that was that I just chose the first value to be the conjugate and I found the second value. This also holds for complex valued eigenvalues. So I don't think you've seen examples of those yet, but if your eigenvalues are like a plus bi, you want to do the same thing. You're going to end up with some term that looks like this, but like this is going to be like I, right? And then your first term here is just going to be the conjugate of it, and you just try to work around the conjugate. Again, the math isn't going to be too great, but it's doable. So that's important to know. What else is important to know? So this is the same thing, right? We worked with the conjugates, so that holds for complex values. Let's see. There's the So I think we did the same thing down here. This one was a little easier, mainly because. So this one's a little easier because these values were 1. So if I take a look at the first row, right? Or if I take a look at a row, my computer's being slow. Anyways, if I take a look at the first row, what you'll notice is that, okay, if I have negative 1, or let's see, if I have 1 times this first value, then I just need the negative in the second value, right? Because then they just cancel each other out. So I did that because so here I didn't do the conjugate thing because I had this negative value. I had the 1s up here. Generally speaking, oh my god, my app's being dumb again. Generally speaking, you would want to use the conjugate thing, and if you use the conjugate thing here, you would have gotten like the same answer, or you would have gotten something that looked different, but it would have been the same thing, just because of how like, you know, the plus square root stuff works out. It would have been fine. Yeah, and then lastly, the important one, I guess, was this one up here. Yeah, with this matrix, right? So just the null space of like all 3s. So what you want to do there is just you want to fix something to be 1, right? So I just fix the first entry to be 1, and then I just try to use the other entries to kill my entries afterwards. So again, if we take a look at this first row, right, multiply by this guy, if the first entry is always 1, then that's going to be a positive 3, and then I just need to get a negative 3 from the other 4 3s. And then so here you'll see that, okay, so for the first vector, I'll just let the first guy be negative 1, or I'll let the second entry be negative 1, and then I'll let the third entry be negative 1, and then I'll let the fourth entry be negative 1, and so on and so forth. So then I can cancel out that 3 in the matrix. So so these are like the tips that occur. I think what really you should probably do is just like practice eyeballing, and one way to do it would be like going back to like maybe like old homeworks or like old matrices that you've seen before, and just see if you can find like different vectors inside. So like for this matrix right here, there are 4 linearly independent vectors you can find, and there are a lot of like bases you can choose. Like for example, this is also in the kernel. You could have done something like, right, 0, 0, 1, negative 1, 0. Like that also would have worked, right? So so I would just go to matrices that you already have a kernel and see if you can find something else. And generally speaking, when the kernel is greater than 0, or when the kernel is greater than 1, then that's where you can have like a lot of freedom in choosing different vectors, because then you're talking about like the kernel being a plane rather than, let's say, a line, which then there's only one vector you can choose. So I think the tip would just be like, anytime I eyeball a matrix, like maybe like try to do it before I do, like in class or something, and then like just go back and just like look at the eigenvectors that you've chosen before and just understand why they're eigenvectors. And once you've seen a lot of them, it just gets easier. As you do more of that. Okay, I'll stay on until 3. I think what I'm going to do is I'll probably upload this at some point, but all the notes are here anyways. So it'll take a few hours for this to like upload because I'm at home and my internet sucks. So you can just go through the notes again anyways. If you need these, again, I'll be here for like the next few minutes. Yeah. Which one? Number 1, A and B. Oh, on the regular homework? Okay. Yeah, sure. We can talk about this. Yeah. I think that's right. I think A A being true, I think makes sense because like how do you get the eigenvalues? You look at the characteristic polynomial, right? Yeah, you like look at the roots of the characteristic polynomial. So if they have the same characteristic polynomial, they're going to have the same roots. Right? So A is going to be true. Yeah, I think all you have to say is that like we find eigenvalues by looking at the roots of the characteristic polynomial. And then so if A and B have the same characteristic polynomial, then they're going to have the same roots. Right. Right, exactly. Exactly. Yeah. And then for B, I think an easy counterexample you can give is the following. So yeah, because it's just a brief justification, right? We're not asking you to do too much, I don't think. So for B, so since B is false, and I agree it's false, you can look at the following justification. Look at these two matrices and compute the characteristic polynomial and then compute the eigenvectors. Because what happens is that since it's a diagonal matrix, so since the first one's diagonal and the second one's upper triangular, right? The determinant is just going to be whatever is on the diagonal. Right? So I think it's general. You can generalize it to diagonal matrices and upper triangular matrices. Right? Because if you have just a diagonal matrix and then you have an upper triangular matrix with the same values on the diagonal, so for example, right, exactly. So if you have like AB and then ACB, right? Like, so this is A minus lambda, B minus lambda, and this is A minus lambda, C, B minus lambda, right? The determinant of both of these matrices are the same thing. They're A minus lambda times B minus lambda. Right? But the whatchamacallit, the kernels are going to be different because of this C. Yeah, exactly. Oh yeah. Yeah, I understand. No, yeah, because if one's just a scalar multiple of the other, then the non-scalar multiple one is also going to be in the kernel as well. So yeah, you don't want to argue scalar multiple. You actually just want to argue like completely like different, yeah, eigenvectors. Yeah. Yep. Yeah. So the notes are already online. So if you go to my website, there should be, yeah, the online notebook, right? They're under office hours, and yeah, they're under office hours. It's like untitled right now, but everything I did should be there. Yeah, no problem. And then I'm gonna upload the recording as well, so that should be up in an hour or two here. Yeah, yeah, no problem. All right. I guess I have 3 viewers left, but I'm gonna end it here. So yeah, like I said, I'm gonna upload the recording. And if you have any other questions, just post on Piazza. I think I at least am monitoring it when I have the time. Yeah. Other than that, thanks for watching the stream. Again, I'll upload these I'll upload the stream in a few hours here. All right.